All right. Hello, everyone. My name is Austin Erickson. I will be giving this talk today on behalf of my colleagues over at the University of Central Florida uh, at the Synthetic Reality Lab. So thank you all for attending. Now, all of you in the audience probably have a smartphone in your pocket or in your hand. We use these types of devices in a wide variety of different environments and contexts. We're using them in very well lit environments, we're using them in dimly lit environments, and everything in between. We're using them while we're walking, commuting, sometimes driving, and static environments and dynamic environments, and again, everything in between. Now, as augmented reality researchers, we have this dream that one day we'll be able to use our AR devices in the same manner. And this means that for each of those other contexts and types of environments, all of those places where we currently use our phones, we need to be able to use those AR devices in exactly the same way. But anyone who's used an optical see-through AR device knows that it's sometimes kind of difficult to see the content on the device depending on what environment you're in. So for example, if you're on the beach and you want to check the weather on your optical see-through device, you may expect that the user interface would look something like this, but in reality it ends up looking something like this. The dark colors of the UI get very transparent. That's just due to the additive nature of the UI. And that's the same way no matter what your environment is. And then the bright white color of the UI also becomes very transparent in this case because of that high level of environment lighting. So we're losing contrast and that UI becomes very difficult to see. Now, in the existing literature, there's been a couple ways to approach fixing this contrast or enhancing contrast in these types of situations. One of them is to change the color of the UI, to adapt to the user's environment based on the appearance of it. So in this case, changing from a white color to a red may improve contrast for the user. And then of course we can take kind of the opposite approach and do a modification to the headset itself and maybe increase the amount of tint on the front of the headset to increase the contrast of the virtual content. But of course this decreases the contrast for all of the other objects in the user's physical environment. So we want to work towards these adaptive user interfaces for AR devices. That way we can reach that dream of ubiquitous AR. But in order to do that, we need to know exactly what the conditions are in which the content starts to become difficult to distinguish. You know, when do we need to use enhancements and adaptive UIs, and when can we get away with using maybe the user's preferences or the developer's preferences for that UI's appearance? So this led us to two different research questions. Our first one is what is the range of environment illuminances in which contrast enhancements should be employed? And then our second is how is the luminance contrast of virtual imagery affected by environment illuminance level? So to look at these, we created a pretty simple experiment where we had an optical see-through HMD positioned directly in front of a dimmable daylight lamp. So these lamps are capable of reaching very high levels of illuminance. We were able to position the two such that we could put a light meter into the headset at the user's left eye position and make illuminance measures from that position. So we're getting an idea of how the light is from the user's perspective. So we set up several conditions. We had 6 different levels of lighting achieved by dimming that daylight lamp. These were between 0 lux and 20,000 lux. We used 2 different head mounts, the HoloLens 1 and the HoloLens 2. These were chosen just based on their availability for us at our lab. And then finally we made 4 different measurements, 4 different sets of measurements for each of these combinations of conditions. So the first was made as a direct measurement of the light, just to establish the illuminance coming from the light. Then we would put the headset down with it powered off to get an idea on how the tint was reducing the incoming light from the user's perspective. Finally, we would turn the headset on and do a measurement with the screen rendering all black or transparent. This was to get an idea on if the ambient, there's sometimes an ambient glow when you have the headset powered on, even though it's not rendering anything. So we wanted to get a measure there. And then finally with the display on and rendering all white. So with those last two measurements, we can calculate the amount of contrast from the user's point of view based on that combination of conditions. So our results look something like this. On the left side, we have the HoloLens 1, and on the right side, we have the HoloLens 2. On our x-axis for both graphs, we have those 6 environment illuminance levels from 0 to 20,000 lux. And on our y-axis, we have the measured illuminance that we got with the light meter from the user's left eye position. So the graphs themselves, the top line, the red and the orange, is when the display is rendering all white, and then the bottom line, the blue or the green, is when the display is rendering all black. So looking at these graphs, we can see that the area between the two curves can be thought of as contrast. And it's at its maximum when we're in those low light conditions, and then it slowly reduces, rather actually quickly reduces, as we increase that environmental luminance up to our maximum levels. So for the HoloLens 1, we see that we have this convergence occur right around 1,000 lux, and for the HoloLens 2, we see that occur right around 10,000 lux. So at those two levels, the contrast is becoming so small that the user is definitely going to have trouble. Of course, an easier way to look at these figures is to convert those illuminance values into contrast values. So we did this using the Michelson contrast equation. So in this figure, we have our y-axis, which is that level of contrast between 0 and 1, and then our x-axis is the same. For the blue plot, that is our HoloLens 1, and the red is our HoloLens 2. So what we can see here is that from 0 to 10 lux, we're achieving maximum contrast, which is to be expected. It's a very dim environment for those two cases, and we're reaching a value of 1 just because the particular light meter that we used is not able to get measurements between 0 and 1 lux. So they round up to 1, when in reality they'd be around like 0.99 or somewhere around there. So as we approach 100 lux, these are kind of the range of illuminances that correlate to very dim indoor environments or dark outdoor environments. So the HoloLens 1 reduces to about 0.3 for contrast, and the HoloLens 2 reduces to about 0.7. Our next range of illuminances is between 100 and 1,000 lux. This roughly correlates to indoor lighting conditions, so it encompasses pretty much all of our working environments when we're indoors. And we can see that the HoloLens 1 reduces all the way down to about 0.05, and the HoloLens 2 continues to reduce to about 0.25. So they're performing okay in this area, but certainly not the best. Then we reach the definite trouble area here. This is the range of illuminances which correlate to very bright conditions. So what you'd find outside on a summer day with the sun out, for 1,000 lux and higher. So again, these contrast levels are reducing. The HoloLens 1 reduces practically to 0, and the HoloLens 2 reduces down to about 0.05. So it's we're seeing this downward trend in contrast as environment illuminance level increases. But we already knew this, right? We didn't need a study to just tell us that. Anyone who's worn an optical see-through headset outside knows that it's difficult to see when you're in a bright outdoor environment. So what are we really gaining from this? So we have two existing sets of guidelines that we looked up here, and one of them is a set from NASA, and the other one's a set from the Australian government, which describe minimum acceptable contrast ratios. So their guidelines say that roughly 30% is the minimum acceptable contrast threshold. So if we look for that value back on that figure, we see that this occurs right around 100 lux for the HoloLens 1 and around 900, close to 1,000 lux for the HoloLens 2. So what this means is that from these guidelines, these two headsets are only usable up to those thresholds, and that the area highlighted under the curves here is the range of illuminances for each of these devices where we need to start employing either adaptive UIs or contrast enhancing measures to be able to better present that information to the user. So these are going to be different for every single display that's out there. And we expect that as more and more optical see-through displays are implemented and we get our hands on them as researchers, similar studies to this are going to have to be repeated. That way we can see the range in which they perform well and the range of illuminances in which they perform not so well. So a couple of concluding remarks here. We saw that the HoloLens 1 and HoloLens 2 are usable up to kind of a threshold limit according to these existing standards. Because of this, we strongly recommend that any studies involving user interfaces and optical see-through AR displays, we recommend that you use a light meter and at least get some baseline measurements for the environment illuminance. These can be obtained from Amazon, very cheap, and the measurements are really quick and easy to perform, and it would give us a whole lot more information as to how these ranges of environment levels affect the user and their interactions with the UI. So finally, we need more research to identify the usability thresholds for the other optical see-through displays, as I mentioned, and this will continue to be a problem as more and more displays are coming out. We need to identify contrast standards for optical see-through AR, and this needs to be done through user testing. It could very well be that 30% standard that we looked at here might not work for optical see-through. We may need a different standard for the specific type of device. And then finally, we need methods of enhancing contrast for optical see-through displays, whether they're hardware or software-based methods. So thank you all so much for your time and for attending my talk here. I will be around in the chat to answer any questions if you're here live. Otherwise, feel free to email me at ericksona@knights.ucf.edu if you have any questions or just want to chat. So thank you again. Bye-bye.